This is lesson 5-5, direct variation. Direct variation is a linear function that can be expressed in the form of y equals kx, where k cannot be equal to 0, but k is the constant of variation. The constant of variation for a direct variation equation, k is the coefficient of x. The variable y and x are said to vary directly with each other. The graph of a direct variation is a line that passes through the point 0, 0. To determine whether an equation represents a direct variation, you're going to solve for y. If the equation can be written in the form of y equals kx, provided k is not equal to 0, it represents direct variation. We'll do a couple of examples here. Is each equation a direct variation? If it is, find the constant of variation. Let's look at the first equation here. We have 2x minus 3y equals 1. The first thing we have to do is we have to solve it for y. We have to put it in y equals 1. So the first thing I'm going to do is I'm going to subtract 2x from both sides of the equation. And I have negative 3y equals negative 2x plus 1. Now I need to divide everything by negative 3. And I will get y equals positive 2/3 x minus 1/3. Notice there's a number that comes after the x. We have a negative 1/3 here. That means that this is not direct variation. In order to be direct variation, it has to be in the form of y equals kx. There can be nothing after the kx part. So this is not a direct variation equation. Let's look at number 2 here. 2x minus 3y equals 0. Again, I have to solve it for y. So I'll subtract 2x from both sides of the equation. And I will get negative 3y equals negative 2x. Divide by negative 3. And y equals 2/3 x. Notice there's nothing after the 2/3 x. There's no number there. Therefore, this is a direct variation equation. And as well as being a direct variation equation, we have to find the constant of variation. K is always whatever is multiplied by x. So if we look at this equation right here, we can see that 2/3 is multiplied by x. So K has to equal 2/3. So it is a direct variation equation, and the constant of variation is 2/3. Last problem up here, 7y equals 2x. It's almost in y equals 1. To get it in y equals 1, I have to divide by 7. So I now have y equals 2/7 x. Again, nothing after my 2/7 x. So it is a direct variation equation, and my constant of variation is 2/7. To write an equation for a direct variation, you have to know the constant of variation. If you know what the constant of variation is, you can use a point other than the origin that lies on the graph, and you can write the constant of variation. So, if I give you a point, you can determine what the constant of variation is, and after that, you can write a direct variation equation. So, if I give you the point negative 3, negative 6, and ask you to write an equation of variation, a direct variation equation, the first thing I'm going to do here is I'm going to figure out what the constant of variation is. Remember, the equation is y equals k times x. The point negative 3, negative 6, we're given the x and the y value because the x value of the point is negative 3 and the y value of the point is negative 6. I can simply plug those into my my direct variation equation to find my constant of variation. So if I plug these in, y, which equals negative 6, is going to equal k, which I don't know, times x, which is negative 3. So to solve for k, I'm going to divide both sides by negative 3 because I have to get k all by itself. So I divide this side by negative 3, divide this side by negative 3. Negative 6 divided by negative 3 is positive 2, and that's going to equal k. So I now know my constant of variation. If my constant of variation is 2, I can write my equation of variation because the equation of variation is y equals k times x. So y equals 2x is now my direct variation equation. Very simple to do. Find what your constant of variation is, plug that into the direct variation equation, you have your equation. Letter B here. Again, I'm going to plug in what I know. I know that negative 3 is x and 2 is y. So if I plug that in, I'm going to get y, which is 2, equals k, which I don't know, times x, which is -3. To solve for k, I'll divide both sides by -3. So k here equals -2/3. So my equation is going to be y equals -2/3 x. And I am done. Last example. Again, plug it in the equation. Y equals kx. Y is 8, so 8 equals k times 12. Divide both sides by 12. K here would equal 8/12, but we can reduce that. 4 goes into 8 twice. 4 goes into 12 3 times, so it's 2/3. So my equation is y equals 2/3 x. And you are finished. So you can now write a direct variation equation if you only know one point on which the equation lies. Now, oftentimes, direct variation equations are used to solve real-world problems in which the dependent variable varies directly with the independent variable. For example, it says a recipe calls for a dozen corn muffins calls for 1 cup of flour. The number of muffins varies directly with the amount of flour you use. Write a direct variation for the relationship between the number of cups of flour and the number of muffins. Okay? So we need to know this. Which one varies with which? It says the number of muffins varies directly with the amount of flour you use. So muffins varies directly with flour. It's probably an important thing to know. Muffins varies directly with flour. That's the first thing we're going to do. The next thing we're going to do is we have to figure this out. We have to look and see if we can find a point. If we can find a point, like the last equations we just did, if I gave you a 0.36, you could write the direct variation equation. Do we have enough numbers to create a point? If muffins varies directly with flour, okay, muffins are going to be y, and flour is going to be x. The independent variable happens to be how much flour you have. The dependent variable is how many muffins you have, because the number of muffins is going to depend on how much flour you have. So x, which is my independent, is my flour, and y, which is my dependent, is my muffins. So it says I will have 1 cup of, a dozen corn muffins. A dozen means 12. I will get 12 muffins when I have 1 cup of flour. So I now have all the numbers that I need to write the direct variation equation. Okay, in the direct variation equation, y equals k times x. Okay. Y is 12. Constant variation I don't know. X is 1. If I divide by 1, k equals 12. My direct variation equation is going to be y equals 12x. Okay. So the direct variation equation is y equals 12 times x. So if I asked you how many muffins I could get if I had so many cups of flour, you could just plug it into that equation and solve for it. Second problem here. The weight an object exerts on a scale varies directly with the mass of the object. Weight varies with mass. If a bowling ball has a mass of 6 kilograms, the scale weighs 59. Write an equation for the relationship between weight and mass. Okay, so the first thing we know is weight varies directly with mass. Weight varies with mass. So we have to have an independent variable x and a dependent variable y. Remember, x is independent and y is dependent. The weight varies with its mass, which means the independent variable is the weight. The dependent variable is the mass. I believe that is correct. All right. The mass. Nope, that's backwards. Stop. Erase. Go backwards. Because if you look at it, it says weight varies with the mass. So whatever the mass is, the weight will vary on that. So the mass happens to be the independent variable, and the weight is the dependent variable. So if we were going to put that into our equation then, y equals k times x, first of all, we have to have some numbers. The mass of the bowling ball is 6, so that would be where we put that. And the scale reads 59, so that's where we would put that. So we're going to have 59 equals k times x, and f dot x is 6, so let's place the x with a 6. Divide by 6, divide by 6. So k is going to equal 59/6. So the equation would be y equals 59/6 x. You can rewrite a direct variation equation y equals kx as y over x equals k. Any equation can be solved for whatever variable you want to solve it for. When two sets of data vary directly, the ratio y over x is the constant of variation. It is the same for each ordered pair. The only reason I say this because if I have y equals kx, I can solve it for whatever variable I want. If I want to solve it for k, I divide by x. If I divide by x, I have k equals y over x. If I wanted to solve it for x, I could divide by k, and I'd have y divided by k equals x. What they're saying is when you have the ratio y divided by x, that's your constant of variation, whatever y over x is. Sometimes it's a whole number, sometimes it's a fraction. You can look at a table of values and tell whether or not it's direct variation, basically based upon looking at the ratio of y over x. Take this first table here. We have a table. It tells us the x is -2, then 2, then 4, and the y is 1, -1, and -2. If we want to know if it's a direct variation or not, all you simply need to do is look at the ratio of y over x. Y over x. So here, y over x would be 1 over -2. This one, it would be -1 over 2, and this one, it's -2 over 4. Well, this equals -1/2. This equals -1/2, and -2 over 4 equals -1/2. The ratios are all the same. Since the ratios are all the same, that means it is a direct variation equation. As long as the ratios stay constant, it's a direct variation equation. So this is direct variation. And I can write the direct variation equation for it because I now know what k is, because k is -1/2. So it would be y equals -1/2 x. Let's look at this second question here. The second table, we're still going to look at the ratio of y over x. So here we have 2 over -1. Here we have 2 over 1. Here we have -4 over 2. This reduces to -2. This reduces to +2. And this reduces to -2. These are not the same. Since they are not the same, this is not a direct variation equation. If they were the same, it would be a direct variation equation, but it's not, so it's not direct variation. The last thing we're going to look at is we're going to look at how you could write different equations. In a direct variation, the ratio of y over x is the same for all pairs. We showed that in the tables that we worked with. So, as long as x doesn't equal 0. So the proportion y1 over x1 equals y2 over x2 is true for the ordered pair of x sub 1, y sub 1, x sub 2, y sub 2. Just means x value of the first point, y value of the first point, x value of the second point, y value of the second point, and neither x sub 1 or x sub 2 is 0. You can rewrite a proportion as an equation of direct variation. And that's what we're going to do in this particular problem. It says, the force you must apply to lift an object is proportional to the object's weight. You would need to apply 0.625 pounds of force to a windlass to lift a 28-pound weight. How much force would you need to lift 100 pounds? Okay. Force varies directly with weight. And it told us up above here that you had the equation, if you remember, way up here, you had this proportion. It's true for any ordered pair. So I can look at this and it basically tells me that force over weight equals force over weight. So if I look at this, the force you must apply to lift an object is proportional to the object's weight. You need 0.625 pounds of force to a windlass to lift a 28-pound weight. How much force do you need to lift a 100-pound weight? All you do is set up a lovely little proportion. It's a direct variation proportion, so to speak. So, if I was to put this proportion into play, all I do need to do is cross multiply. So if I cross multiply, if you remember cross multiplying solves your proportions. So if I cross multiply, I have 28 times F, and that's going to equal 0.625 times 100. So 28F equals 62.5. Divide by 28. F will equal 2.23 pounds. And so I need 2.23 pounds of force on a windlass to move a 100-pound weight. And a windlass is like a lever. So there we have it. And this is basically what direct variation is talking about.